Good morning, everyone. I'm Vinitha, working as an associate professor in the Department of Electrical and Electronics Engineering, RMD Engineering College. Today, I'm going to explain about load flow analysis. So, first, let us see what is mean by load flow analysis and why load flow analysis is required. This load flow analysis, which is otherwise called as power flow analysis, which is very important in power system, and this power flow analysis, which is necessary for the planning of power system, economical scheduling, and control of an existing system, control of an existing system, as well as the future planning of the power system. That's why we require this power flow calculation. And the main information obtained from this load flow analysis is the magnitude and phase angle of voltages at each bus and the active and reactive power flowing in the each line. All those parameters will be calculated from this load flow analysis. Formulation of load flow problem. So this load flow problem is the most fundamental study which is to be performed by the power system both during the planning and operational phases, and it constitutes the major portion of electric utility. And here, this power system, that is, this power flow analysis can be done under balanced condition. So, what is meant by balanced condition? That is, during operation of the system, the voltage between all the three phases should remain same, and the frequency must be maintained as constant, and then the phase angle between all the three phases must remain same. So these are all the conditions to operate the system in balanced state. And after solving the power flow equations, we can determine the bus voltages as well as the power flow in the given network. And after calculating this power flow analysis, the present status of the power system required for continuous monitoring that will be analyzed, and what are all the alternative plans for the system expansion to meet the ever increasing demand. So in order to obtain the future expansion and then continuous monitoring, this power flow analysis which is essential. And this power flow analysis that will be analyzed, that is, this will give the uh, this mathematical formulation of the power flow problem results in a system of non-linear algebraic equation. So these power flow analysis can be an iterative technique for obtaining the solution. And here there are various methods available to obtain this power flow equations. So first one is Gauss-Seidel method, and second one is Newton-Raphson method, and the third one is fast decoupled method. Among all the three, this Gauss-Seidel and Newton-Raphson method that is most commonly used method to get the power flow equation. And here, for this power flow solution, actually, we require the following steps actually. So the first point is nothing but we have to draw the single line diagram. Then after obtaining the single line diagram, we have to draw the impedance diagram from the single line diagram. Then we need to form the network equations. So after forming the network equation, the solution has to be obtained by solving the power flow equation. These are all the basic steps we need to follow while solving the load flow equation. In this power flow equation, there are four quantities are analyzed. So one is the magnitude of voltage, and the second one is phase angle of the voltage, and then real power as well as the reactive power. Now let us see the classification of buses in this power flow analysis. And here there are three types of buses with respect to the factors of real power, reactive power, magnitude of voltage, and del angle. And here PA is represented as the real power which is injected into the bus, and QI is the reactive power which is also injected into the bus. B is the magnitude of the bus voltage, and then is the phase angle of the bus voltage. Among these four quantities, any two quantities will be specified for the bus, and the remaining two quantities that will be obtained after solving the load flow equations. Here the types of buses are specified. The first bus is called a slack bus or swing bus or reference bus, and one of the generator bus that will be taken as the reference bus. And for this reference bus, the magnitude of voltage and the phase angle of voltage that will be specified. And after solving the load flow equation, we need to find out the remaining parameters like the real power as well as the reactive power. And the main purpose of providing the slack bus is to calculate the transmission line losses in the network. And the second type of buses is called as load bus, which is otherwise called as PQ bus. So from the name itself, we can say the quantities P and Q will be specified for the load bus. And after solving the load flow equation, the magnitude of voltage and the phase angle of the voltage must be calculated. And the third bus is called as generator bus or otherwise called as PV bus. And this bus is called as voltage controlled bus or otherwise called as regulated buses also. And here also it is represented by PV bus. So PV bus means the real power P and the voltage magnitude of voltage that will be specified for this generator bus. And after solving the load flow equation, we need to calculate the parameters like Q as well as del angle. And here the same type of buses that will be tabulated. And here the first bus is slack or swing or reference bus. In this, the known parameters are V and L, and the unknown quantities are P and Q. Similarly, for a generator or voltage control bus, P and V will be specified, and we need to calculate the value of Q and L. And the third type is load or PQ bus. For this bus, P and Q will be specified, and V and L must be calculated. And that is given that these three type of buses that is represented in a simple single line diagram. Here I told that the first bus, normally one of the generator bus that will be chosen as the slack bus. Here this generator bus, that is the first bus that is chosen as a slack bus. For this bus, the quantity specified are nothing but V1 and L, and after solving the load flow equation, P1 and Q1 will be calculated. So what does this one represents? So one represents first bus. Similarly, second bus. So it is a generator bus. So since it is a second bus specified in the problem, we can take this as a second bus P2, Q2, V2 and Del2. These are all the parameters for this generator buses. For the generator bus, P and V will be specified, and we need to calculate the value of Q2 and Del2. And the third bus is nothing but the load bus. So load bus, which is otherwise called as PQ bus. So since it is a third bus, it is represented by P3 and Q3. Here, for this load bus, P3 and Q3 will be specified, and after solving the load flow equation, we need to calculate the magnitude of voltage and phase angle del. And now let us see why the slack bus is essential. What is the need for this slack bus? Actually, in power system, normally which will have only two type of buses like generator bus as well as the load bus. But in the power system, actually, the generated buses as well as the load power that will be specified. But nothing is specified to calculate the losses. So in order to calculate the losses, the slack bus, which is essential, we know that in power system, some of the power generated that is equal to some of the load power plus the transmission line losses. From this expression, we can calculate the value of transmission line losses. So how to calculate transmission line losses? From the total power generated, if we subtract the load demand, we can able to calculate the transmission line losses. So only to calculate the transmission line losses in power system, the slack bus is included. Now let us see what is in the flat voltage profile. This flat voltage profile is nothing but an initial voltage that is assumed for an iterative process. So as I said earlier, here the methods used in load flow analysis are nothing but iterative methods, and so here the initial voltage is assumed, and this voltage which is assumed for all the buses except the slack bus, and so this voltage which is called as flat voltage profile. And next one is acceleration factor. So what is mean by acceleration factor? What is the need to include this acceleration factor? So since it is an iterative process, we have to speed up the iterations. So in order to speed up this convergence process, an acceleration factor is included in the system. And here the acceleration factor is 1.6. So if we multiply this acceleration factor with the value or whatever the solution we got, we will the system, that is the system, get accelerated, and so that it will converge quickly. And generator buses are treated as load bus. Normally in power system, we have load bus as well as the generator bus. In the generator bus, we have to calculate the value of Q, and we have to check whether the value of Q that lies within the specified limits. If it lies within the specified limits, then we can consider that bus as a generator bus, or otherwise that will be considered as a load bus. And there will be various iterative solutions for power system model. One is Gauss-Seidel analysis, Gauss-Seidel method. Second one is Newton-Raphson method. Third one is fast decoupled method. In this Gauss-Seidel method and Newton-Raphson method, that will be important, and we are going to discuss about these two methods. And here for this power flow problem, we can write the basic equations. Here in this is a bus. Bus is nothing but number of elements that is connected to a common bus. And here this is a generator bus and this is a load bus. And at the bus, VI is nothing but the voltage specified at the bus. Current is nothing but the I is nothing but the current drawn from the bus. And the complex power, which is represented by SGI for a generator, it is represented as PGI plus J into QGI. And the power drawn from the bus is SDI, that is equal to PDI plus J into QDI. And the total power at bus I can be represented as SA is equal to SGI minus SDI. So what is SGI? PGI plus J into QGI. And similarly, we can substitute the formula for SDI. So since here we have minus, the expression is minus PDI minus J into QDI. And we can separate the real power and reactive power. So the real power is PGI minus PDI plus J into QGI minus QDI. Therefore, S can be written in general as Pi plus J into Qi, and this can be written as S is equal to Vi into Ia star, where the value of I that varies from 1 to n. It is nothing but number of buses. And here we have I star, but we require the current II, because for analysis purpose, if you take I star, it is we need to go for its complex conjugate. So in order to avoid that, we can take the value of II, so that for the entire equation we can multiply by complex conjugate. So Pi minus J into Qi, that is equal to Vi star into Ia. So from this equation, we can easily find the value of IA. IA equal to Pi minus J into Qi divided by Va star. We know the equation for I is equal to Y into V. And if we write it in the matrix form, we can write I1, I2 till In into Y matrix into V matrix. Here the value of I that varies from 1 to N. Therefore, in general, the net current that entering into the ith bus can be written as IA, that is equal to YI1 into V1, that is I is equal to V by Z actually. 1 by Z is nothing but Y. So that we can write the expression in this manner: YI1 into V1, YI2 V21 plus till Yin into Vn. From this, we can write in general, we can write Ia is equal to sigma k is equal to 1 to n Yik into Vk. Now we can substitute the value of Ia in equation number 1. Therefore, we can rewrite the expression as Pi minus J into Qi, that is equal to Vi sigma k is equal to 1 to n Yik into Vk. And where real power is equal to, we can take only this real part, And if you want to calculate the reactive power, Qi can be written as here, since we have minus in the left hand side, we can write this as Qi is equal to minus imaginary part of the same equation. And if we want to write it in the polar form, we can write the expression as Vi equal to magnitude of Va angle of del I. And similarly for the kth bus, we can write Vk magnitude of Vk angle del K. And for Yik, it is written as magnitude of Yik angle theta Ik. And where theta Ik is nothing but the admittance angle. And from this, we can write the equation in terms of rectangular form. Pi minus j into Qi, that is equal to modulus of Vi angle minus del I into this entire term. And Pi minus j into Qi, that is equal to Vi sigma k is equal to 1 to n Yik. We can rewrite the above expression Yik Vk angle delta theta Ik plus del k minus del I. That is, we are taking all the magnitude separately, and we are adding all the angles separately. Therefore, from this we can write the entire expression for Pi minus j into Qi, that is equal to modulus of Vi sigma k is equal to 1 to n Yik Vk cos of this equation can be written as cos of theta Ik plus del k minus del I plus j into modulus of Vi sigma k equal to 1 to n Yik Vk into sin of theta Ik plus del k minus del I. So these are all the basic expressions. Now, if we equate real part and reactive imaginary part in the previous expression, we can calculate the real power Pa and the reactive power Qi. And the power injected into bus I is in general written as Pi is equal to Pg minus Pd, and Qg is equal Q and Qg minus Qd. And here, the equality constraints for this load flow analysis which is given. So for the equality constraint for power balance condition can be written as sigma I is equal to 1 to n Pgi, that is equal to sigma j equal to 1 to n Pdi plus PL. That is, generated power is equal to power demand plus transmission line losses. And similarly for reactive power. And inequality constraint. In some of the cases, the power generated power will not be maintained as constant, so that it may vary. So here PGI, which is specified within the minimum limit as well as the maximum limit. Similarly, QGI that lies between QGI minimum and QGI maximum. So these are all the equations we have to study while solving the load flow equations. Thank you.